So our first speaker is Marek Bożejko. His mathematical great-grandfather is David Hilbert. Then his mathematical grandfather is Steinhaus. And his PhD advisor is Stanislav Hartmann, Stanislav Hartmann. He received his PhD in 1973 at Wrocław University. He got his habilitation in 1980. That's what I found. And in 1984, he won a main prize of research from the Polish Mathematical Society, Stefan Banach. So that's a great honor. Marek Bożejko is an expert in free probability and harmonic analysis and applications. A highly cited paper is called Q Gaussian Processes, Non-Commutative and Classical Aspects. And today he will talk about the generalized Yang-Baxter operator, Fock spaces with applications to quantum probability and quantum channels. So please, Marek.
O, teraz. One. No. Coś tutaj nie chcę. A, coś tutaj. Co? Okay. Okay. So, thank you once more for invitation and for so nice presentation. I am very glad that can speak. I never was yet on IWOTA conference, so it was my great pleasure. But I work with a lot of people from that community, and so I'm glad that you allowed me speak about really harmonic analysis. I am a specialist, but of course, recently harmonic analysis on free object like free group or free product of groups or some other, a lot of application to operator space and to famous for Neumann inequalities and so on. So my talk will be really devoted to method and give you method of what I use. Main method is some kind comes from application Yang-Baxter matrices. So I never saw in any talk, but maybe I'm a mistake. So Yang-Baxter, we introduce some generalization of that. Yang-Baxter, I say to you in a moment, this is generalization of commutativity, that matrix T1, T2 is equal to T2, T1. This is commutativity, but Yang-Baxter is a little bit extension. T1, T2, T1 is equal to T2, T1, T2. And that is like braid relation. That was discovered from, at least from statistical physics. Probably everybody, maybe not everybody, but almost everybody knows the famous book of Baxter, exactly solved statistical models. If you never read that or never look, you are not on this world. You should look for Baxter. Young obtained Nobel Prize, that is the co-author, Yang-Baxter, and that is really understanding what is in mathematics. Anyway, but method, what we found is using wide groups. Wide groups, this is like discrete part of skeleton of continuous group. For example, SUN group, special unitary group, have this skeleton, this is permutation group, SN. When you have quaternionic or you call this with J matrix some correlation, that is type B Y group, but this is nothing else like sign permutation group. And I speak only about that Y group and method what I apply. Maybe you can use in your other application. Unfortunately, as you see, this is my handwritten, so that maybe in future that will be showing, oh, you see, only Bojejko talk was really written by mathematician, other written by secretary, because by computers, yeah. So this is like in history, when you look for documents, if you written hand, this is document, but this, anyway, let's come to, and method, what I found is related to famous, I never also saw in your talks. This is Cauchy transform or Stieltjes transform. This is moment generating function, more or less. Yeah, this is just like moment generating function. This is exactly for moment, let's say probability measure or some other, 1/z moment generating function. Yeah, this is exactly Cauchy transform or Cauchy Stieltjes, or some people call here Riesz transform, tra-la-la-la-la-la. But when I was about 50 years old, nobody said me, I say to you now, also maybe, that this is related to the continued fraction. Continued fraction was discovered by Stieltjes, that famous Stieltjes. And he developed that, let's say, analytic function as a continued fraction, not continuous series, no, continued fraction, and that is 1 divided by z minus alpha 1 minus lambda 1, z minus alpha 2 minus lambda 2. That coefficient are called coefficient for orthogonal polynomials. For orthogonal polynomial, for that measure orthogonalizing that case. So if you have measure with integral Pn x, Pm x, dmi x is equal delta Nm, some coefficient, this is really lambda 1, lambda n. So that orthogonal polynomials, that coefficient appears exactly in that continued fraction, and vice versa. This is fantastic method. Of course, here is a lot of combinatorics, a lot of, by the way, business. When you look for Stieltjes paper, Stieltjes, famous paper, he wrote maybe 100 or more exams. When he discovered this, of course, he has not like now theorem. He just take measure, concrete measure, like Gauss measure, or some other measures. I'm sorry, I don't prepare on my, but when I found in all talks here, no, continued fraction, I say, I should say 5 minutes, say to you. Yeah? So the famous is the measure, the Wigner measure.
I just want to encourage people to move to the middle of the room and also a little bit in front so that you can see the whiteboard. Right.
Sorry. Mm-hmm. I should, but yesterday was excursion and I couldn't. Anyway, Wigner measure, so this is measure is semicircle and this is 1/2 pi integral 4 my x squared dx. Yeah. This is the Gauss, free Gauss. This is Gauss which appears in free probability. That Gauss, this is fantastic object. An orthogonal polynomial, this is famous Chebyshev polynomial of second kind. And the continued fraction, when I call this measure me, let's say for Wigner, W, so the continued fraction, of course you can calculate this, but this is what I called gold, 1 divided by 1 minus 1, z, 1 minus z, 1 minus z. You see such a continued fraction called gold number if this is equal 1. But this is gold, so this is gold measure, gold object. Okay, and for example, when you come to the classical Gauss, it's not so interesting so much, but maybe also for you. So when you have, let's say, classical Gauss, the famous measure e to the minus x squared divided by 2 divided by square root of 2 pi, that measure is Cauchy transform. This is x, is Cauchy transform of this. Is, you know, this is Hermite polynomial, and this is just 1 divided by z minus 1, z minus 2, z minus 3, and so on, because lambda n is equal n. In my talk, important will be q, the formation of that, q, where this is equal q to power n minus 1 divided by q minus 1. This is q Gauss. This will be q Gauss. Among this, when q 0, you obtain that measure. Anyway, so this is introduction. So that method is very useful, and I like that you remember this and give to your students and to yourself. Calculate today at least one Cauchy transform. Okay, so let's come now to talk, because this was beginning. It's not in plan, but time is coming on. So what I should do? Probably I should come down. I should now page down. Okay. Okay, so this is just what I sent to the organizer that written on computers, my plan or abstract. As I see, I thought that 50 minutes is a lot of time, but it's not this case. Anyway, I have in plan considered classical and generalized Yang-Baxter operator related to Y group or Coxeter group, like permutation and psi permutation. The most result, what I would like to present to you and his many application is positivity. Because that people which know me, I believe only in positive numbers. I never believe in zero even, but only positive numbers. And positivity, positive operator, this is object which exists, yeah. Of course, we can use negatives, this is like science fiction. So this is my result, and we prove very general result using positivity for almost O Y group, or even more for O Coxeter group, and I say a few words of this. And then that Gauss, from this we obtain a lot of Gaussian measure. That Wigner measure, what, discovered by Wigner? No, by Chebyshev, of course. Chebyshev discovered polynomial in that measure. Of course, Professor Wojkulescu discovered this as a free Gauss in central limit in free probability. And I will speak about this maybe a little bit in application. We have extended with Speicher to some free probability to other, and also my colleague Wojtek Młotkowski even more, to your case, because you like operator version business. And what I have, I say some few words about orthogonal polynomials, which are important. So, of course, everyone knows Hermite. I don't know if you know Q-Hermite. I know everybody know what is the Q-Meixner. This is like Poisson, some generalization, but also Askey-Wimp Kerov. This is very nice class discovered by many people. And I see what, and at the end, if I have time, of course, some inequality appears here because you like inequality. So I show you Chebyshev inequality, which is true for O contraction, but non-commutative. So my inequality will be only for n equal 1. And as application, I have to, because now is very, how to say, important time of quantum information. So this, we found a lot of quantum channels, which is important. I don't know, people say to quantum computing, tra-la-la, tra-la-la. Okay, so this is my abstract talk. Of course, this will be my, how to say, lecture for one semester. So this is, but yeah. Okay, so what is Yang-Baxter matrix or operators? Usually people say matrix. If you look for Yang-Baxter book, so this is in language here because main object here is a Hilbert space, yeah? Finite, you like 2, 3-dimensional, is even that is important. But mathematicians like abstract Hilbert. So really this was discovered by Baxter, but important role play when Jimbo, the famous Jimbo and Voronovich, they would start quantum group about, I don't know, 40 years ago. They observe that this is main object to deformation, because quantum group is nothing like deformation of classical group, like topology is deformation of the cube or something like this, yeah. So, and that operator is just acting on tensor product of 2 Hilbert space. And we have different type. Now I show to you type A, this corresponding to permutation group, to type A Y group or Coxeter group, and satisfy, I don't know, this is work, this? No. Maybe this way. This is not, okay. So delta condition, that means that R12 times R23 R12 is equal like R23 R12 R23, when R12 is just extension of our matrix A, operator R, to tensor product of 3 copies. Yeah, 3 copies of R, of H. And of course, when you see this is, as I said, generalization of commutativity. Yeah? You allow me, maybe I take away, especially ladies, my wife said me that I should start officially, but now I'm a mathematician, I'm working. Da się zrobić coś? And the typical example, what we found in my life, and also in the Jimbo start with the simplest case that 1B, R matrix, or they call R matrix sometimes, yeah, that is when you have basis A, I, A, J, this is Q times A, J, A, Y. So transposition times Q. Of course, it's more interesting, more natural when you take more, so in a moment will be some other examples. Anyway, so this is natural object. And why this is natural? Because in a moment will be my picture. So this is important because this is kind that parameter Q or some other parameter like Qij or some more general with some other parameter. For example, the famous Young paper, look, his Nobel Prize paper is 2 pages. But he discovered real Yang-Baxter matrix. Okay, so this is, okay, oh, fantastic. Good. Of course, there is a, tak może być, okay, it's okay. And now this is discrete case that was using in the quantum group, so maybe some model of Yang-Baxter, but we observed maybe 10 years ago with Janusz Wysoczański and Zhenya Litvinov that continuous case is very important, and this was the problem by, okay, tak tu idzie do góry, tak? W prawo, w górę. W drugą stronę, okay, okay, okay. Okay, so the continuous case, I'll be not coming to that. Maybe continuous case is important also here. So, so I take continuous, like Euclidean space, and that R matrix is on tensor product of L2 on, let's say, Euclidean space with Lebesgue measure. And that R matrix or Yang-Baxter matrix operator is just multiplication not by discrete but by continuous kernel QXY. Yeah. And for the application, of course, the most important is when that modulus of that function is 1. I don't come to details, only this is example. Okay, so now let's come further. Okay, and how we discover, that was discovery for you very easy because you teach permutation group. So permutation group really is group which is symmetric group, of course, of triangle and other beautiful Platonic solid like simplex. And that is group with the so-called wide Coxeter generators are very simple one. just generated by inversion, but very special inversion. Only 1, 2, 2, 3, tra-la-la-la, up to k, n minus 1. You know? And when you look for S3, so this is the simplest symmetry of the triangle, when you look for Cayley graph, so you start identity, and that P1, P2, and from right side you multiply by the only relation what is in that group is Yang-Baxter. You see from left side is P2, P1, P2, but from right side is P1, P2, from left side. So P1, P2, P1, this is bad written. So this appears very natural, because for me, permutation group is that hexagon is enough. And you please teach your students like this. Okay, and that operators appear natural. Of course, with deformation, you have, that you make that graph make some weight, you know, put weight or something like this. So, okay. But what I would like to say yet today is another important object symmetry. The symmetry group not of the simplex, but symmetry group of the cube, n-dimensional cube, discrete cube. And that, I don't know if you teach your students, but this is sign permutation group. So this is just permutation together with the plus minus, yeah? So, so really that object is the subgroup of permutation of plus minus 1, plus minus n. When they are odd, the sigma minus k is minus sigma k. And of course, this is skeleton. Maybe there are people from like quaternions, so Clifford. This is skeleton of special unitary quaternionic group. So, you know, this is very natural. Of course, if you like quaternion, I like very much, because Hamilton for me was genius like Gauss. Okay, and the main object here, this is the inversion, 1, 2, 2, 3, tra-la-la-la, like permutation. But of course, by symmetry is 1, 2 to minus 1 to minus 2. But there is another coming from quaternion structure, or you call it J matrix. It's minus 1, 1. And that group, when you make group generate, is the symmetry group of the Platonic cube. And that is the main. Of course, there is a subgroup type D with subgroup of length 2. This is the very famous Platonic groups. Of course, but that groups are very special kind of so-called Coxeter Y groups. Coxeter, I even wrote his name because it was Harold Scott MacDonald Coxeter, and Weil his name Hermann Klaus Hugo, like Hugo Steinhaus. Weil, I don't know if you know this. Hermann Weil was genius also. And they introduced group, which this is they call now, we call Coxeter group. How is the time? Oh, okay. Maybe I don't come to detail, but that group is generated by orthogonal reflection in Euclidean space. Yeah? So here I wrote, so that have relation like this is not pointer here, yeah? Okay. So this is relation, just, you have generation, finite generating sense, S1, S2, Sn. Every is reflection, so square is equal identity. And this is the famous Leonardo da Vinci theorem that when you take two different reflection, composition is just rotation, Mij. And so, okay. Oh, thank you. So this is the reflection here. And this is the Leonardo da Vinci. That combination of two reflection is just rotation. And that is only relation. We don't need more. And that is, of course, this was not the time of Coxeter and Weil, but now we know that this is abstract definition of Y group or Coxeter group. But that Mij, oh, sorry, I'm just, that Mij can be arbitrary integers bigger than 2 or equal to. So for commutative group, just is equal to. Yang-Baxter is 3. And now we come for hyperoctahedral, the symmetry of the cube will be, Mij will be 4, yeah, and so on and so on. Okay, so maybe I don't come to details. What is the reflection? Everybody know orthogonal reflection and some relation. So maybe I put away this from my, anyway, this is okay. And now let's say this, yeah. And important for my result, because I would like to have positivity result here, prove that operator connected with Yang-Baxter positive operator, so positive matrix. We need length function done by a set of generators. So this is minimal number K when words W. You can draw a minimal way as a basic SIMB, we call SIMB reflection. Yeah. If you know root system, this is SIMB roots. Yeah. Okay, and proposition which is done in Bourbaki book is that length function is just number of P, this is the SIMB roots time inverse, W minus 1 of minus P. Yeah, okay, and then I should come down, so this. Yeah, and then what is this theorem? This is the main theorem what I today would like to say to you. This is theorem about generalized Yang-Baxter matrix operator. That we have a lot of authors. Really, this was done by Roland Speicher and me, but then we extended by my colleague Richard Schwartz and Tadeusz Januszkiewicz. There's many other applications. But what is Yang-Baxter the general sense? That is just, Yang-Baxter is that equation. That function is generated really for the group, but is enough to say on generators, and then extends. Extension is multiplicative. So if you know what is on S1, S2, tralalala, S1, S2 will be product. Yeah? And that the multiplicative, I call quasi-multiplicative, is just that if length is just sum of lengths or not cancellation, is product. This is like homomorphism, but it's quasi-homomorphism. Yeah? And of course, you should assume that that phi is, as an operator, is self-adjoint because we need positivity even. And I claim that that map phi, if you consider on O group, or even C-star algebra, if you like some formal language, to B of H is completely positive defined function, completely positive. So this is that news what I suggest you, maybe you can use in your word. What I should do? Yeah. No, I did make something. So anyway, this is yet about sign permutation group. I'm sorry. This is that important, yeah. And that should be written is positive definite. Completely bounded even. Completely bounded. It's not only positive, but completely bounded. No, I don't explain you what everybody knows what is completely bound. And that is a lot of application. So what I should do, this is application, no, the other side. This is for wide group. I will not say too much. You can, permutation, another example, yeah. Length function. Maybe I don't see this another positivity result when we use another length function which connected with the flux, but maybe I okay, and first application. Why this operator is important? Because we would like to have CCR relation and CAR relation. This is the main object on, let's say, mathematical physics or application everywhere. This is Gauss, Brown-Noun motion, tralala. So this is equation was in one lecture of one professor important, that is relation with plus. So when Q is equal minus 1, we obtain a relation. So you have two family of operator, AF, A star G, and you have commutation relation when parameter Q and the scalar product F G. This is, and that was nicely explained when Voiculescu came to free probability, and he has observed that free probability is when parameter is 0, when Q is 0. So Q 0, and that is so-called Joachim-Kunz relation. So this is Kunz relation, in Kunz algebra is related. Yeah, but how we can construct? Because problem is, okay, you can write, and most of physicists, mathematicians wrote, let it be. You should prove that exists such an object, yeah? And proving existing, this was our theorem with Speicher. We proved this, and for this we need generalized symmetrizator, generalized Yang-Baxter. Yeah. So we need the operator PQN with another Q, or maybe Yang-Baxter matrix. Oh my God, this is something. I should do this not. Okay, so that PQN, maybe I wrote here, I can blackboard. So this is reason that I like blackboard, that I can say to you reality. Good. So what is the symmetrizator? Of course, this is generalization of symmetrization of when you construct symmetric and antisymmetric matrix of tensor algebra. Okay. So what is the PQ? So you even more general P. So you have phi on, let's say, permutation of Y group. Take first a permutation group, B of H, and you take symmetrizator. So you have that P phi on N. This is operator of N power of H to N. And that operator is just done by formula. P phi N is summation phi of sigma, when sigma is in permutation group. But of course, you can here write any Y group, any Coxeter group. And then when I take parameter Q and the simplest operator T, Yang-Baxter T of xy is equal Q times yx, we obtain the simplest, the Q deformation. This is called twisting with parameter Q. And then you introduce new scalar product. For Q equal 1 is symmetrization. For Q minus 1 is anti-symmetrization. Okay. But what is interesting for other cases, for the that group symmetry of cube, that diagram, Dinkin-Coxeter diagram is, you know, you have just here P0 is P1 tralalala, this is permutation, but P0 is that quaternionic matrix, like J. And then we have, can you put two parameters? Yeah. One parameter you can put for Q for that permutation business, but for P0 you put some another parameter, or Yang-Baxter matrix, you know. Only here you need Yang-Baxter matrix, not like I wrote T1, T2, T1 is equal, but I should wrote more general. T2, T1, T2, T1. This is type B. Type B, Yang-Baxter. Of course, when you have considered more, you have more general relation. And what is surprising, that we have theorem for all Coxeter group. I don't understand this. I know proof. I have many proofs. But this is strange. Yeah. I ask you, help to us, because we proved this with Speicher maybe 20 years ago. And now students use tralala, but we don't understand to the end. Yeah. Why such a beautiful groups can have such a beautiful property? Okay, so when we put this, so what we get, we obtain another relation. We work this, so this is with Speicher, what I say you, but now, oh, sorry, so this is another direction I come. Sorry, yeah. Of course, I said also to another, and that we work with my colleague, Victor Eismond also, and Hasebe and other people, a lot of group. I say you later, is a group working on this. Also type D is the, I'm not coming to that, but also is interesting. And then we come to Meixner-Polacek. This was probably Czech. Yeah, Polacek was not Polak, not Polish. Meixner was German. I prefer you don't read about him personal things. He was together with Hitler. Such is life sometimes. Okay, and then we obtain the measure. What we measure? So we should define it Gaussian. I have no time to speak, but we have to Meixner-Polacek polynomials, which appears naturally as a Gaussian. This is Gaussian measure. Only not in classical probability, classical aspect, but with that hyperoctahedral or quaternionic aspect, when you have two parameters. What is interesting that the measures are, of course, is normal law when alpha, when q is equal 1, but when, well, I should do this down. No, this. Oh my God. Anyway, so under other parameterization, I will not because I wrote, you obtain some other interesting measure. For example, when q you put 0, that has a place, and that's we so-called Kesten measure. It's very famous Kesten, maybe for everybody, Harry Kesten is. This is not only probabilist, but also important in the random walks on graphs and so on and so on. And this is that family. And this he discovered when he was student of Marek Katz. This was his PhD degree. Marek Katz was from Lvov. This was Lech Maligranda speak about, but he was his student. Yeah. Anyway, that measure is important. I have no time. Of course, when you look for Cauchy transform, you obtain this is like a silver measure. Yeah, but I have no time. Anyway, you should, okay, Meixner Polacek, tra-la-la-la. But this was observation what we did with Hasebe and Eismont, that when you put alpha minus q to 2 gamma, I don't know why, we just trying, we obtain, as with reparametrization, we obtain such a polynomials which are like classical Meixner when q is equal to 1, but there's some generalization. Okay, so, yeah, so, okay. So now application. So I would like, I have yet some time, because we start 5 minutes later, so I remember, 7 even. Okay, but you believe me that I would like speak. For me, 1 hour is nothing, you know. Okay. So application, this is Khinchin inequality, which is more or less, I don't come, this is some paper we wrote recently with Wojtek Mutkowski and Światłosław Gal for Coxeter, Coxeter group. But Pizier asked also for permutation, prove this. So we prove Khinchin inequality. What does that means? That means that, and that is important. So we would like, because you work in non-commutative business. So why, when you have matrix, you use commutative random variable? This is some sense, I would like to say that you are on wrong direction. You should come to non-commutative. Yeah? Of course, and the simplest non-commutatives, free Gauss, like Wigner matrices, some random matrices are okay, you can use, but with special property. And then the more important object is just for scalar, that when you have such an object, we define it for set of, let's say, operator AS, some set S, this will be seemed reflection, object like L2, but Schatten class norm, SP, this is non-commutative LP. So I'm glad that here on that symposium was Schatten. By the way, Schatten was student of Banach, Stefan Banach. His first name was Rubin. This was on Tog Maligranda, because I asked him, and he came to Lvov and he said me. So Schatten, this famous co-author with, or collaborator of von Neumann and so on, and probably everybody knows cross norm of Schatten, if you are young, a little bit younger than me. Okay, and that is the norm, what was defined, this called row and column, and that is new direction. I have no time to speak about non-commutative function, but Viktor Vinnikov was saying, we have some talk also. So this is notion of LP. Of course, for matrix, you have Schatten norm, but for the more object is the row and columns. So you consider row and columns. And what is the result? The result is, let's say this, I should use this. Yeah. So I take as a, that should be here Gaussian, and this element, and I don't know how to do this. Maybe it's too wrong, but maybe I have found some method. Oh, very good, very good. Operator Khinchin? Ah, excellent, thank you. Thank you that you helped me. So, and that is our object, you know, and I claim this is the first step to understand your business. Come to objects which are like here. For example, here is Coxeter group, doesn't matter, Coxeter system. But important, you take LP norm on like Schatten, and coefficient AS from Schatten class. Yeah? And what is this? If it's scalar, this is famous Kinchin inequality, left and row, this is L2. Yeah? When it's scalar, this doesn't, but here, you distinguish left and right, row and column. So especially matrix in row or matrix in column. Okay. And then we prove, of course, this result was proved, I think, by Pizier, Hagerup, for free group, and anyway, but we observed this is work for for all Coxeter group. That's why I was surprised, because Pizier, Marek saw me for permutation group. So we start and we prove for all, of course, thanks to my collaborator, Wojtek Mutkowski and Galo. Okay, so we prove this. For lambda FS is a left regular representation, so it's very non-commutative case. So, and I appoint to us that in your job, if you appear such a row and column, you should be happy, because it's the simplest so-called non-commutative Banach space, I would say, or operator space, some people say. But of course, this is not the best. The best is so-called OH. I have no time to speak. This is universal Hilbert space. And it's open problem, find in nature OH. And even for two. This is so, Efros called this quantum Pythagoras triangle. Anyway, so let's come further. Yeah, and the constants play a role, because if constant is different, the groups are not isomorphic, it's star algebra. So because such a problem appears in that people business, so maybe also in your. So at least we prove, of course, I don't say, but the simplest Coxeter group is Rademacher. It's group generated by Rademacher system. So mathematician called plus Z2, plus minus 1, plus minus blah, blah, blah. This is Rademacher. Discovered the later Cantor put to infinity, yeah? Or maybe before. And then and the best constants, even in operator sense, found my student Arthur Buchholz, very beautiful result. Okay, this is that constants. And also Gerolf Händler from Heidelberg discovered for the Coxeter when this exponential is bigger or equal 3. So this is like free case. We don't know why. Good, so let's come further. Yeah, so I have yet some time. Good, I have time, I'll be not hurry. So I should say to you some joke, probably, if I be American. So
you have 10 more
10. Oh, merci, Mr. Chairman, yeah, okay. So as I say, I lost a lot of transparent because I work, as everybody know, I like only blackboard or maybe white. White is not because, anyway. Okay, so some applications. So application to quantum channels will be done by a generalization of free probability of Voiculescu, will be done with Speicher and Leinert from Heidelberg. And later Wojtek Mutkowski extended this also very nicely. So what is quantum channel? So we are in some star algebra with unit, and some state that Voiculescu called this abstract probability system or something like this. But to have channels, we need completely positive map yet from that algebra to bounded operators. I don't know if you have lectures of channels of quantum computing. Of course, everything is finite dimensional, but we don't assume anything. So, and what is quantum channel? So we have two states. We have a state on that algebra A, which usually is trace, yeah? So usually is a trace. So that phi is a trace, and psi is a trace, and phi is a completely positive map. This is the channel. Yeah? And the finding of channel is a difficult job. I give you some example, maybe. And the main result will be that free product of channel will be again quantum channel. So this is our result just recently. So what is quantum channel? This is just that pair, phi, completely positive map, and small psi trace on the algebra A, with trace preserve that completely positive map. This is called channels. Why channels? Because it's beautiful property. And have some application. This is not my notion. This is, You can have Cholevo. There is a book a famous book I recommend you, Stanisław Szarek and some group of his collaborators called Alice and Bob Meets Banach. Such a book, its title is Alice and Bob, this is meets Banach. So this is not my computer now. So then you have a lot of examples of the quantum channels there, but yeah. So fundamental for me I'm coming from group, of course, for harmonic analysis. So take group algebra, for Frobenius algebra, so linear combination of elements of the group. Here I take Fock-Coxeter group, but this is because I know result. Yeah, because I need completely positive maps, yeah, to be channeled. And such a map was discovered first by Poisson on the integers. This map on sigma is q to the n. Yeah, this is the famous Poisson kernel. Yeah, Poisson positive definite function for q between 1 and 10. And that theorem was extended by Uffe-Hage group to the Fripp group. I extended to Fripp product, and this is beginning of so-called Boolean probability. Anyway, don't come to this. So we take such a capital phi. This is completely positive maps. If there is, that group, for example, is Weil, Coxeter free group. Not for all groups. Q to the length is depending on the length and depends on the group. Yeah. So, of course, it would be nice to prove that for every group, there is a system of generators and that length function Q to the length is positive. I'd be very happy. Maybe. And we take as a trace, von Neumann trace. By the way, this von Neumann discovered this 100 years ago. This was the first observation that each group has always trace. This is Haar measure, dual of Haar measure. Yeah. Now people in quantum group, they use very often this. The Voronovich called this discrete quantum group. Okay. So this is the channel. And we define it now, another example. This comes from second quantization for bosonic, fermionic, free, and we deal with Speicher and Kummerer, what Professor mentioned on your introduction, a paper about non-commutative business. This is so we take real contraction on Hilbert space, and we define it second quantization, gamma q of t, such a way that on so-called weak product is just W F1 Fn is just natural way. Of course, when you discuss with physicists, they forgotten the W. They say just act on each component. Yeah, here you can. And that weak product is just is not C here because it's just in my private computer. Weak product is for these people which work on the group. This is so-called symbol of operators. So this is such a weak operator WF is just on the vacuum because we usually have some Fock space and some fixed vector, like on group is identity, yeah? on semi-group is identity or Fock space. And that is just the symbol, F1, Fn. Yeah? And then you can prove that if Psi is trace defined by vacuum expectation, projection on the vacuum, that really the triple for any real contraction, that this is quantum channel. Quantum channel is, so we have example. So this is quantum channel that when I remember, this is the vacuum expectation, and this map completely positive is not so trivial to prove completely, always completely positivity somewhere. Because, you know, positivity is easy, usually, scalars. But then you can extend to matrices, yeah. That whole conference was on matrices. I'm very happy. I learned a lot. So thank you very much. Okay, so let's come further. And now main theorem of my talk today. I have yet 5 minutes. Even more. 3, let's say. Sorry. Okay, so main theorem is that if I have a quantum channel, yeah, here is a quantum channel AI, Phi, Psi, and we take conditional product, so we have free product of the algebra with respect Psi, I. This is Voiculescu like this, and we have Psi is just conditional business. This was done first, I think, by Wojtek Mutkowski. That strip is again quantum that the free product that, and we define psi, capital phi, as a product if psi of aj is 0. This is like Voiculescu-Frines, but this is operator version that we call conditional free product. That the theorem, this is again, yeah. Another application, 1 minute, for Neumann, because for Neumann is important. So I of course, work for Neumann 2, for 1, 2, 3, people say no, but I prove for every. So I take any family of contraction, T1, T2, T3, T5, okay? And I take non-commutative polynomials, PR, Z1, Z2, Zn, with coefficient scalars, and I put just P of, on the variable, I put just, instead the variable, I put operators. And then theorem is that is less, norm of this is less than supreme over unitary matrices. So, and this is of course norm of sister algebra of free group. But on the finite matrices, of course the famous proof for 1, n equal 1 is like this, that you extend to unitary, you have spectral theorem, tra-la-la, you have. But here for 2, that for 3, for many, as you want. P0, the lecture knows about this, so you can, sorry. And how we prove? We take the famous Nyberg contraction, or completely bounded. So for contraction, we put a function on integers, e to power n for positive, for negative, e star to minus n. And then we extend multiplicative, and that, if you take free product of this, this is published, so you can find Bojeko for Neumann inequality, but non-commutative version. I wait, of course, for the commutative version, and I wait that some of you send me information very soon that, like Professor Conrad said, that is not true. No, it's true, only, okay, so I have, of course, a list of my colleagues which work, but probably you have no time. 1 second. Mr. Chairman, so this is last my paper, what I say that it's conditional free probability. With Gutta, I would say maybe this is type B. Most of them are publication, communication, mathematical, physical journal, functional analysis. That with Hasebe is some other business. Sorry, so this is not that case. I should, anyway, so at least I take part, so you can see my papers, but I wait for your remarks, and thank you once more that Mr. Chairman give me 1 minute or more. Thank you, and thank you also. Sorry that I mostly take to that part, but I don't know how to work with, we have 2 parts. But thanks you also you for the nice atmosphere. And some of you sleep, but I understand. After such a beautiful dinner, yeah. Okay.
Thank you very much. Thank you.
Thank you.
Any questions for Marek? Yes. Tito.
For the completely positive map that you and Speicher constructed from Coxeter group to BH, is there a Steinspring type dilation theorem?
You can treat this. Of course, Steinspring is for every completely positive map, you have dilation, yeah. But I use here, but maybe you are right, we can use more general result to abstract. But as you know, I like completely positive. Concretely, no, I think that maybe it's chance to use Steinspring general result for completely positive, and I don't try this, but I agree with you, and maybe we can think more.
Is it even possible to formulate this result in this case? Because on the left-hand side you have a group.
Maybe, I am coming from harmonic analysis.
Okay.
In that time, this I did like 20 years ago, or 15 or 10 years ago. I don't like the abstract, My students know that if you don't give me example, addio, please come with example. Because some people say, I have theorem. No. You should have 5 examples at least to have theorem, yeah. So thank you anyway for your question. I will be thinking maybe together with.
Any other questions here?
So at the beginning you mentioned this continued fraction expansion for the Cauchy transform. In the case of operator valid Cauchy transforms, do you also have something like that? And also for your Q Gaussians?
For some special. That Stiltje theorem, if I know, works for special deformation only, when, for example, only lambda 1 is operator. That will work. This is okay. When lambda 1, the coefficient lambda 1 is that Wojtek Motkowski, I think he don't remember this, but this. So you can do this, but for general, there is another continued fraction done by Gelfand and his collaborator. I think in advances in mathematics. I always say to my student, why you don't do this? Because even Cauchy transform for 2 measure on the plane is open. How to should be done? Because no problem of what should be analog of orthogonal polynomials. You know, we have Chebyshev polynomial of 2 variables. That should be model for, of course, Wigner law, 2 variables. I ask many questions. And, no, this difficult. Cauchy transform is only for unitary or normal, tra-la-la-la. But should be. I am sure that what you say should be true.
How about Q Gaussian?
Q Gaussian, we work with classical, and that what I say for Q Gaussian measure is theta 1 function of Jacobi. Not Jacobi, Jacobi. Jacobi from Królewicz, Königsberg, now Kaliningrad. Yeah. So, that is, but scalar, but operator version, I think maybe Wojtek Motkowski, but he worked moments on and not Cauchy. As you know, there are some problems. I discussed with Belinsky, and we work some problems. And matrix is difficult, even for 2 by 2. Okay, okay.
Let's do one more question. Victor, please.
Let's see. Yeah, it works. So I just wanted to mention that there is a version of the non-commutative phenomenon equality due to Popescu. It might be slightly different because it's not the kind of what you compare is not the C-star algebra of the free group, but the rather free semi-group algebra. So.
No, I know. Yeah. No, yeah. This is also a nice direction, but something like one-sided, like you see.
It's isometric dilation rather than
I met just recently Żelu Popescu, and but his direction is just phenomenon inequality in different direction. Maybe this is right. I wait for phenomenal for OH of PZA for that universal Hilbert space, which dual is the same object. Because the row and columns is dual, in sense operator, as you know, is not the same. But there is such an object, very difficult one, like quantum triangle, quantum simplex, which is a real object. And thank you for the Żelu. I forgot to say, because this, of course, if I have 1 semester, I will speak everything. Thank you very much, Victor, and nice to see you. And you make also propaganda of that, what Efros called quantized function analysis, yeah? So what we are doing?
No, quantized function theory.
Maybe quantum. You know better.
Okay. Well, let's thank Marek again for a wonderful, inspiring talk.
Thank you very much.
And very soon we'll start with the next lecture. Thank you.
Thank you.